Okay, so hello everyone. Thanks for coming. Today we are very excited to have Cynthia here. So Cynthia is Earl McLean, a junior professor of computer science and electrical and computer engineering, statistical science, mathematics, and biostatistics, and bioinformatics at Duke University. She directs the Interpretable Machine Learning Lab, whose goal is to design predictive models that people can understand. Her lab applies machine learning in many areas of health, such as healthcare, criminal justice, and energy reliability. Also, Cynthia is the recipient of the 2022 Squirrel AI Award for Artificial Intelligence for the benefit of humanity from the Association of Advancement of Artificial Intelligence. So it's a very big bio. There are many good things here. So we are very excited to have you to this very interesting talk. So thank you very much for accepting the invitation. And the stage is yours, Cynthia.
All right. Okay, cool. So my talk is called Simpler Machine Learning Models for a Complicated World. And as you just found out, so my lab at Duke is called the Interpretable Machine Learning Lab. And one of my most important goals is to create machine learning models that are small enough to fit on an index card, yet are as accurate as the best black box models. And, like deep neural networks, right? So you're probably thinking, is this for real? Can you actually do this? Because this would mean a lot for trustworthy and fair machine learning if you could do this, right? And the answer is yes, we can totally do this for a lot of important problems. And we think we now know under what circumstances you can do it. You can't do it for computer vision or speech, but you can do it for many other problems. So I'll give an example. Okay, so a few years ago, there was a competition sponsored by FICO, which is the major credit scoring agency in the United States, as well as Google, MIT, Oxford, Berkeley, and others. It was called the Explainable Machine Learning Challenge, okay? And they gave everyone a data set from FICO, and the goal was to predict whether someone would default on a loan based on their credit history. And they told everybody to create a black box model and explain it because they didn't think it was possible to create an interpretable model with the accuracy of a black box for such a complicated data set. But several years after the competition ended, my team figured out that there are accurate interpretable models. You just have to look for them carefully. Okay, so just to tell you a little bit more about the data set, it's got about 10,000 loan applicants from a particularly difficult subpopulation. And like I said, the goal is to use credit history to predict whether somebody is going to default on a loan. And again, it uses data from the major credit scoring agency in the United States. And at the time, which was 5 years ago, nobody produced a really tiny interpretable model that was as accurate as a black box, right? People produced tiny models, but they were not accurate. And so we produced something at the time that was a combination of these tiny models, but the overall model wasn't tiny. But 4 years later, which was last year, we produced the first small models that performed as well as the black box models for this data set because we had some new powerful machine learning algorithms that could do it. And because the models fit on an index card, they also fit on a PowerPoint slide, so I can show them to you. So the first model that I'm going to show was produced by the fast sparse algorithm from our lab, which creates sparse generalized additive models. And this work was done by Jiacheng Liu, Chudi Zheng, Margaret Seltzer, and I. All right, so this is the whole fast sparse model for the FICO dataset, so right here. And you get a score for each of the variables, so you just look up your score, and you just add up the total scores for all the variables, and that score translates into a risk for defaulting on a loan. So let's just take a look at some of the factors here. So months since oldest trade opened. So if your oldest trade was pretty recent, then you get more risk points because you're riskier. And if your numbers of satisfactory trades is kind of small, like less than 10, then you get more risk points. And this particular variable, external risk estimate, this is very sensitive to values of this variable between 60 and 80. You see it designated a whole lot of little steps in there. Okay, so what's really shocking about this model, besides its simplicity in describing this very difficult benchmark data set accurately, is that we created it in under 4 seconds. And that's about how fast this algorithm runs on average. It runs in about 4 seconds on this data set, right? It used to be that finding interpretable models was so computationally expensive that we couldn't do it at all. And now we can do it in just a few seconds. All right, so let me show you now a different type of predictive model for this data set. This one's going to be a sparse decision tree created by the GHOST algorithm. So GHOST stands for Generalized and Optimal Sparse Decision Trees. And it was developed by our lab over the course of a decade. I've put up pictures of the army of people here that we've had working on GHOST. GHOST is very fast. It's orders of magnitude faster than the previous approaches for optimal sparse trees. And this is the GHOST tree for the FICO data set. So let's just take a look at it. So this tree, again, it's just as accurate as the best of the black boxes. And what it says is that if the external risk estimate variable, which we know is important already, right, from the other model. So if this thing is too high or too low, then we make a prediction. Okay, so if it's too high or too low, we make a prediction. Otherwise, it's kind of in the middle in that sensitive range. Then we have to ask these more detailed questions, like how many months since the most recent inquiry? Well, let's exclude the last 7 days, you know. Okay, so I just want to point out how difficult this model is to create. Your algorithm has to figure out all kinds of stuff, including all of these little thresholds, which variables go in which spots, even the size of the tree, where the leaves are, where are you going to grow, okay? So it's actually, it's actually computationally hard to do this. Like if you're familiar with computational hardness categories, this is NP hard, there's no polynomial time approximation, and yet this was created by GHOST in 8.1 seconds, which is really impressive. This is actually the same tree as on the previous slide, but it's done in like a more artistic way. This year we participated in the Bell Labs prize competition and we needed a really beautiful title slide. And so this slide was designed by an artist friend of Margot's. That's why it looks so cool. So like this predictive, like this powerful predictive model just kind of growing in nature. So I find interpretable models much more natural than black box models. Black box models might be kind of like snarls of branches or something like that. All right, so what I'm telling you is that even on competition data sets, we find interpretable models. Now, if people are not using interpretable models, what are they using? Well, they're using black box models, which are difficult, either too difficult for a human to understand, or they're proprietary, which means there's somebody's secret sauce, okay? And so if they're too difficult to understand, they can't be put on a PowerPoint slide. All right, so what's wrong with using black box models? Well, they are difficult to use in practice. So here I have an example from criminal justice where a typographical error into someone's risk score calculation prevented them from getting parole. So a typo determined freedom, which is not how our justice system is supposed to work. And also, black box models are difficult to explain. Here's an example from loan decisions, right? So if you want to know, like, okay, my loan was denied, I can't buy a house now. Why did that happen? Well, the black box model, difficult to explain. And also, black box models are difficult to troubleshoot. This is an example from healthcare. Healthcare is like a huge can of worms. This article is about a FDA-approved deep learning model for detecting intracranial hemorrhages, and then they launched it in practice and it didn't work, and nobody knows why. And it was approved by the FDA, okay? All right, so yeah, black box models in healthcare, they deserve their own slide here because they cause so many issues. Like, first of all, you have this situation where the model is right, but for the wrong reasons because of some correlation, like predicting that someone won't have a good outcome based on their x-ray. But instead of looking at the x-ray, the algorithm just looks at which machine the x-ray got taken on. So the medical decision ends up being based on which x-ray machine the person was getting their picture taken on, which is not good. But since you don't understand the reasoning of your black box, you just don't know whether this is what's going on or not. Also, you have these high stakes decisions. You don't really want to leave them to a tool that doesn't really understand the whole situation. Also, it's really difficult to troubleshoot black boxes. You can't second guess the reasoning process of them because you don't know it. So is it going to work if I switch equipment? It's going to work for all types of patients. Can I check if it's working on my current patient? Is the information that I fed into the system correct? Right? With black boxes, it's really, all this stuff becomes more difficult. And then you have questions of responsibility or accountability, right? Who is making this decision here, the human or the machine, right? It's the doctor's responsibility to make the decision. All right, so black box models just turn what would be computer-aided decisions into automated decisions. Okay, so black box models really shouldn't be used in healthcare if at all possible. All right, so if black box models are bad, why do people still use them? Well, first of all, people don't believe that interpretable models can be as accurate as black box models. It doesn't matter how many examples you give them. When a new problem comes along, they go, oh, this is probably something that needs a black box. And I can understand this for domains like that really benefit from neural networks like computer vision or speech, but even if it's in a domain that has never benefited from neural networks, they still think this. Also, people really like black boxes. Black boxes can be someone's secret sauce. Like, you can sell a black box. You can't really sell something that fits on an index card, right? You got to sell the mechanism to collect all the data from the patients and combine it behind the scenes and so on. Also, interpretable models are hard to create. Actually, I'm going to try to convince you today that they were hard to create, right? But traditionally, they are hard to create. I definitely don't, I'm not sure I can handle the politics on the secret sauce stuff. So, but I can definitely help with the first one and the third one. And so, let's start by discussing the third one here, that interpretable models are hard to create. Okay. So, the reason they're hard to create is because of this interaction bottleneck that arises when people realize that interpretable models have interpretable flaws and they need to fix them. So let's say that a doctor uses data to produce an interpretable model, right? The doctor looks at the model, which now they can do because it's understandable, and they find that it doesn't align well with what we know about medicine. So what do? Right? The machine learning algorithm gave them this model, and so the doctor's stuck. Right? Even if there were hundreds of millions of equally accurate models, right? The algorithm only returned one of them. And so stuck with it, okay? So these models, they're all equally good with respect to the data, right? With the data you got, there's literally no way to tell which of these models is better. The only way to tell the difference is with domain knowledge, but there's no easy way to put the domain knowledge into the algorithm. And that's the problem. There's no feedback loop, right? Machine learning algorithms return only one model at a time. And interacting with machine learning algorithms is a problem that the standard machine learning framework is just not equipped to deal with. So we need an entirely new machine learning paradigm at this point because machine learning is totally broken here. All right, so my collaborators and I decided that, the standard machine learning framework had to go. And so last year we proposed a new paradigm for machine learning. It's something that's more human facing than the standard machine learning, which is to hand the user all good models from a given function class, not just one model, and let them choose which model they want so they can pick something that doesn't just agree with the data, but also agrees with their domain knowledge so they might actually use it. And we call this set of good models the Rashomon set, okay? Now, I'll point out that doing this is extremely technically difficult because finding even one optimal model is provably hard. But now I'm saying that we have to find all of them and store them, even if there are hundreds of millions of them, and we have to visualize them so the user can choose from them. So this is not easy from a technical perspective, but it's extremely useful in practice. And it changes the whole notion of machine learning from just being about optimization to being also about enumeration and storage of the Rashomon set and also visualization of it. All right, so let's show an example because we now have the first algorithm that computes the whole Rashomon set for a non-trivial function class, which is sparse decision trees. And like I said, Margot and I and our students, we've been working on variations of optimal sparse decision trees for 10 years. And so now we can solve these optimal sparse tree problems very quickly. So this is an example of a ghost tree on a criminal recidivism data set. It's on the famous COMPAS data set. The algorithm in the new paradigm is called tree farms, okay? So tree farms doesn't just find one optimal sparse tree like ghost, but it finds all of the optimal and slightly suboptimal trees for any reasonably sized data set, and it displays them in an interface called TimberTrek. So I'm gonna bring up TimberTrek. I'm just clicking there and it's gonna bring up TimberTrek for me, and I'm gonna switch the sharing so that you can see what I'm looking at here. So I just clicked on this and it opened a website. So I'm not doing anything that you can't do. I just went to a website. Okay, this is the website for TimberTrek. So TimberTrek here is storing all of the optimal and slightly suboptimal decision trees for the COMPAS data set right here. And you can search through them. Like if you want only trees where like the top split or like the first decision, the first question you ask is the number of prior crimes greater than 3, then you can just click there and it just limits you to just the trees where the top split is number of prior crimes greater than 3. And then if you want the second question you ask to be like, is your age less than 26? Then you can do that, and that limits you to those trees. And if you find a tree that you particularly like, you can just store it. You can put a little heart on it. You can write a little note on it, like, I like this tree. It agrees with my domain knowledge or something like that. And then you can also display the tree based on the number of data points going to each side. So here you can display it like this, where like about a quarter of the data points are going this way and like 3/4 are going that way. And then another thing that you can do also is if you decide you didn't like what you your decisions that you made, you can go back up to the top. And then let's say that you like so one really nice thing about the new paradigm is that you can incorporate constraints very easily, because all you have to do once you have the Rashomon set is just sort through the models in the Rashomon set and find the ones that obey the constraints. So it makes things like fairness, like computational fair, like algorithmic fairness, makes it really easy. So for instance, as an easy constraint, you could for instance, let's say that you didn't want to include a sensitive variable like sex equals female, then you can just click that and it just reduces just the models that obey the constraint that it doesn't have that particular variable in it. But you can do all kinds of fancy algorithmic fairness constraints if you want, or monotonicity constraints or anything like that. Okay, so nice things about this setup: there's no more interaction bottleneck, right? It makes the feedback loop to humans essentially instantaneous. And as I said, it allows you to incorporate constraints for free. So I hope you're starting to see the value in this new paradigm, right? It's a lot more computation up front, but it completely annihilates the interaction bottleneck and constraint handling. Okay, so let me tell you a little bit about how it works. I'm not going to go into detail since it's really complicated. The first step in the tree farms algorithm is to run the ghost algorithm. So ghost will find a decision tree that minimizes this objective over here, which is misclassification error plus a regularization term times the number of leaves in the tree. And you really do want this regularization term here, because otherwise the tree, like even if you have like a depth constraint, you still want this thing in here, because otherwise the tree might have unnecessary splits in it. So you really want to keep that term there. So you run ghost, you get the a minimizer, and then you want all the trees within epsilon of ghost's optimal solution. Okay, and that's the Rashomon set, and that is what tree farms is going to find. Okay, so the key ingredients for tree farms are a dynamic programming formulation and theorems that reduce the size of the search space so that the dynamic program dead ends all the time. So you don't have to search that part of the space, because you can prove that large portions of the search space of trees do not contain any element of the Rashomon set. So these theorems involve finding lower bounds on the objective function from the previous slide for lots of different subtrees, and passing that information kind of upward through our data structures. Okay, now the third element is what we call the model set representation, which is our data structure that can efficiently store hundreds of millions of trees. And it stores them in this implicit way so that you can enumerate them, but what you store is parts of trees that can combine with other parts of other trees, so that the storage is actually much more compact than storing all the trees one by one. It's much, much, much more compact. Okay, so you might be wondering if we actually need something as fancy as tree farms, right? Can we get the Rashomon set just by sampling lots of trees? So we asked, do other methods produce all almost optimal models? And as it turns out, they do not. So just to show you an example, on the Monk2 dataset, tree farms finished creating the Rashomon set in 46 seconds. So we tried running some sampling methods for 46 seconds. So in 46 seconds, Bayesian additive regression trees created 488 unique trees. And how many of them were in the Rashomon set? Only 3. Random Forest created over 20,000 unique trees. 0 of those were in the Rashomon set. CART on random bootstrap samples of the data created over 20,000 trees. Only 7 of them were in the Rashomon set. And then we can compare that to tree farms, which provably provides the whole Rashomon set, and it gave us over 105 million unique trees. So we would have no idea that the Rashomon set was quite that big if we didn't have tree farms. And we get very similar results on other data sets too. Okay, so all right, so we've made a lot of headway in fixing this third issue, which is that interpretable models can be hard to create. And so let us switch gears and talk about this first issue, which is that people don't believe that interpretable models can be as accurate.
Cynthia, I have a question. Can I?
Oh, sure.
Yeah. So in your algorithm, like, can you guarantee that you pick all Rashomon set trees, or is there like a probability that you don't pick?
No, it's a dynamic programming method. So yes, you pick them all. The only ones we don't pick are the ones that are trivial. Like, you could take a tree and extend it by one leaf and have them both vote positive, right? That's silly. You would just collapse it to leaves. So we omit those trees where you've got extra stupid branches for nothing. But yeah, we're provably getting all of the optimal and slightly suboptimal trees. That's the benefit of dynamic programming as opposed to something like gradient descent.
Oh, I see. Thank you. So another question is, like, what is a sparse tree? Sorry, not sure.
Sparse tree has a small number of leaves.
Okay.
So these are all sparse trees, right? These are all sparse trees because they only have a few leaves.
Okay, I see. So is necessarily true that sparse trees are always as good as like bigger trees, or not necessarily?
Yeah, that's what we're getting to.
Okay.
Yeah. So they seem to in a lot of problems, right? It's not going to be that way for vision or speech or anything like that. But these sparse trees, even for the FICO data set, which is a competition data set, it's able to do, very well. We were able to get just as accurate as deep neural networks with a sparse tree, which is sort of like, oh, why is that? Okay. And so, so like I said, so people don't really believe the evidence from these data sets. And so, yeah. So, yeah, I mean, look, I've been presenting examples from real data sets about the existence of interpretable models for a decade, right? And people didn't believe that then, and they still don't believe it, okay? So if they don't believe the evidence from data sets, I figured, well, maybe I could try to convince them using a mathematical proof, okay? So the goal became to prove that interpretable models are likely to exist for data sets with specific characteristics. And so that way, by knowing something about how your data set's generated, you should be able to know right then and there, before running any algorithms, whether this is going to work, right? So in order to get us into the right frame of mind for this, let's just talk about the universe of supervised machine learning problems, okay? So there are really two different worlds of machine learning based on the kind of data that you're working on. So most people think these two types of problems are the same, but they're fundamentally different, which is probably why people are getting confused. Okay, so the field of machine learning has mostly focused on these raw data problems like vision and speech and language. And here you can make really complex models like deep neural networks, and they actually generalize between the training set and the test set. But for tabular data, which is the kind of problems that I've been showing you, if you try to use a really complex model, it's not going to work. It's just going to overfit, and you're not going to see the benefit of that extra complexity. Now, there's one important difference between these two problem types, which is that the raw data problems tend to have certain outcomes. So for image recognition, for instance, we know whether an image contains a chair, right? So it's possible to get over 99% accuracy in identifying chairs. But most data-driven problems in the world, they're not like that, right? They have uncertain outcomes, like the FICO data, or like consider two medical patients with very similar medical histories. Right? One might have a heart attack next year, and the other one might not. Right? Deep learning really hasn't had an impact in these kinds of problems, and I believe I understand why it actually can't. Okay, it's not about whether we have the right algorithms. It's just something different about these problems that just always allows us to find accurate, simpler models for them. And here's a simpler, here's like a simple visual example in 2D. So here's a clean data set where you can fit the data perfectly and everything's fine. But then as soon as you introduce a bit of unpredictability, what we call noise, then boom, you just overfit. Okay, so Leslie Semenova, Ron Parr, and Harry Chen and I have written these 2 papers, which together aim to give at least some semblance of the beginning of a mathematical proof that noise actually causes this whole thing. Noise is what leads to large Rashomon sets, and large Rashomon sets lead to the existence of interpretable models. And so I'm going to just show you a picture at the bottom so you can kind of see what I mean. So you can see like this noisier data. This is the Rashomon set for the noisy data set, and that's the Rashomon set for the clean data set. And this one looks clearly bigger than that one, okay? So this theory is a little bit hard to understand if you are not a machine learning expert, but I'm going to try to explain it. So bear with me. All right, so the first step is that noise in the world leads to increased variance of the outcomes and increased variance of the error. I used to think that if you took a clean data set like this and added a bit of uniform random label flipping as noise, then predictive error for all the functions would just go up by an equal amount, and all the good models would still be good, and all the bad models would still be bad. But that doesn't seem to be true. And in fact, it's completely false. So when you add noise, the variance of the labels increases, which means that the variance in the error increases since the labels go into the error function. So the error gets hard to estimate. Okay, so the error definitely goes up, but you can't estimate very well what's going on. So all of a sudden, you just can't see anything. You're like in this cloud of uncertainty smog. And we've been able to prove that this happens for special circumstances. So for instance, we proved it for label flipping, uniform label flipping uniformly at random. We've also been able to prove it where the probability of the labels flip depends on X, and margin noise where you like smush 2 Gaussians together. And all of them have increased variance of the error with noise. Also, this higher error variance, that actually leads to worse generalization between training and testing. And you can see that from a theorem based on Bernstein's inequality. So generalization bounds like this, they're not perfect, but they tend to have the important quantities in them. And in this case, it's the variance of the error. And this bound is tighter than Hoeffding's inequality, which is typically what's used for generalization bounds. So we know it's pretty tight. So what I'm saying here is that the loss variance, the error variance, that's a really important quantity in generalization, and it's increasing. So anyway, the model doesn't generalize. Okay, but the analyst is not stupid, okay? The analyst, they're not just going to use an overfitted model, right? The analyst can actually see this happening because they're using a validation set. So the analyst compensates by simplifying the function class. All right, now, when the analyst simplifies the function class, the new class has a larger Rashomon ratio, which means a larger fraction of good models. So the fraction of good models goes up. Okay, so why is that? So as you go to more and more complex function classes, you have more good models than you did before, because your good models from before are still good models now, right? But you just have more models, so more of them, you have more good models. But you also have, but the number of total models goes up really, really fast. So you all of a sudden, for these more complicated function classes, you have tons and tons of bad models, and the number of good models is tiny in comparison, right? And this happens because each good model that's in the simpler function class gives rise to a few good models in the larger function class, but the bad models in the simpler class don't really give rise to many good models. They give rise to mostly bad models. Okay, so for instance, with decision trees, the simpler class is small trees, and the more complex class is larger trees. And so the good smaller trees, they can grow into larger good trees, but they also grow into a lot of bad trees, since there are usually a lot of bad options, but not as many good options, right? And the set of bad trees doesn't really grow into good trees all that often. So the set of good models is large now relative to the function class with these simpler model classes. Okay, and we actually have 2 proofs for this. We have one for decision trees, and we have one for ridge regression. So now we have a large fraction of the function class being good models. I mean, not like half or anything. It's less than 1%, but you still get the idea. And so now we have a covering argument. So the set is large, right? Large enough to include a ball inside of it. And then we say that there's an even simpler function class, like simpler set of models that serves as a good cover for the space. Like, like if you think about, you could think of shallow decision trees covering the space of deeper decision trees. So it's like covering it or representing it. And then from there, since there is this big ball of good models right here, then you have a simpler model within it. Okay, so you've got a model that's even simpler and it's also good. And so by this argument, you can get quite simple models that perform well. And so that was the last step, right? Which is that when you have a large Rashomon ratio, simpler models are likely to exist by this covering argument. So that's the proof. Now, one nice thing about this mathematics is that the practitioner never actually needs to know how much noise is present for this to work. Okay, they don't need to know that. It just sort of works. Okay. Oh, we have a question.
Yeah, hi. Yeah, sorry. I just have a one quick question. When we are creating this Rashomon set, then we need to have some threshold, right? Like how much accuracy deviation should we allow? So in practice, do you have any recommendation that how much you should allow to create a Rashomon set or something like that?
Yeah, it's usually like 1 or 2%. So or you could do up to 5%. I mean, it gets to be difficult to calculate when, I mean, you're talking about the practical stuff, not the proof, right? So yeah, so in practice, I would do between 1 and 5%, depending on the problem.
I see. And in the proof, probably we will see a balance between them because larger the bound, more elements will be inside the Rashomon set. So
Yeah.
yeah. Thank you.
Sure. Okay. So I've just told you about the Rashomon set theory, and the implications for this theory are pretty intense, because the implications are that optimizing for simplicity won't sacrifice accuracy for a vast set of problems. It's actually any problem where there's noise and when you can't predict perfectly. Okay, so hold on one second. Okay, sorry. All right. So yeah, so you can get a sense just by knowing this one thing about how the data are generated, whether or not simple yet accurate models can exist. Okay, so if I'm right, this has huge implications for a lot of high stakes decisions that are made using data in our society that deeply affects people's lives. And this includes criminal justice decisions that determine people's freedom, and loan decisions that determine someone's ability to purchase a home, or medical decisions that determine life or death. Because if I'm right, then for none of these decisions can we really justify black box models. For none of them. And it's not like we didn't know this already. I mean, for instance, now interpretable AI models also have a precedent in high stakes healthcare decisions. Like this model, for example, that's the 2 helps 2B score, which predicts seizure risk in critically ill patients. It's the only AI model that's used in critical care brain monitoring, and it was developed by our lab. In terms of, let's talk about criminal justice. Do we need black box models here? My first paper on this was in 2017, so I've been studying this for maybe 8 years, and tiny little models do just fine for this, even on data sets that consist on over 40,000 people. I don't see any good reason why we should allow black box models in the determination of someone's freedom. And for loan decisions, I already showed you models built on the FICO dataset. Both were built in under 10 seconds, and they're about equally accurate to black box models like boosted decision trees and neural networks. Right? If the major credit scoring agency in the United States provides data that they don't think can be handled by interpretable models, and they're wrong, think how many others are also wrong about this. Okay, so far, I've shown that even on competition data sets, we find interpretable models. I've talked to you about the Rashomon set paradigm, where our goal is to find not just single models, but whole Rashomon sets, which solves the interaction bottleneck and constraint handling. And I've also gone through this sort of idea of a mathematical proof, which is our path to simpler models that starts with noise in the data. And That proof consisted of really the argument that trying to predict outcomes that are uncertain leads to large Rashomon sets. Large Rashomon sets imply that simpler models exist. And of course, this has huge implications for criminal justice loan decisions and other high-stakes decisions. Okay, so where do we go from here? Or at least where do I go from here? Well, I think one thing that our work could help with is regulation. I think that we should have no black box models for high stakes decisions that deeply affect someone's life unless there does not exist an equally good interpretable model. And we know that, that's not very likely to happen with problems with uncertain outcomes. Also, the performance comparison between the interpretable models and the black box models should be done in practice and not on a static data set. It should consider the whole system, not just the predictions, because you want to include the ability to troubleshoot and get the inputs correct and so on, right? And that will really show the advantage of using a model that people understand, because then they could troubleshoot it. And we should not have any stupid explanations of black box models. We don't just want to know which variable is important. We should be able to demand to know exactly what went into this decision. But regulation is taking too long. I mean, I was really happy to see President Biden's executive order last week, but it's really only a start, and we don't truly have really any regulation of AI right now. So anyway, we're just, I'm not just going to sit around and wait for regulations in order to do something. So what I'm working on now is expanding the Rashomon set calculation to include additive models. And we're also using the Rashomon sets for variable importance calculations. We call this XAI on steroids. So our variable importance measure, it's called the Rashomon importance distribution, and it estimates the true variable importance, like the variable importance for the data generation process, and not just for one model. And it works by averaging variable importance across the Rashomon set and across bootstrap samples. So it gives you a much more stable measurement of variable importance, like a much more holistic view of variable importance than what the XAI world is doing, which is looking at how important one variable is to one model. And this slide is about our latest method for risk scores called faster risk. Risk scores are like the 2 helps 2B score or the CHADS2 score or the APGAR score, right? These are used in medicine a lot. These are sparse generalized additive models with integer coefficients. Scoring systems are very simple model forms. You just add up the points and it translates into a risk using a table. But these are notoriously hard to construct because you have both sparsity and integer constraints. Like these are the coefficients, they have to be integers. And so that makes it kind of doubly NP hard. This is faster risk's result on the FICO data set. It loses a little bit of accuracy over fast, sparse, and ghost, but it's so crazy simple. Anyway, we have a bunch more methodology work going on besides these, but let me switch over to applications. So we're working on material science applications, so interpretable materials discovery with machine learning, as well as I'm still working with the team where we developed the 2 helps 2B score. I also run a lab that does observational causal inference using matching algorithms. So we develop matching algorithms for estimating treatment effects. And so we're combining the 2 to try to predict the effect of the drugs on these critically ill patients to try to get better drug policies. And then we're also studying, I have a group of students that does dimension reduction for data visualization, and they also, that seems to be quite useful for genetic data. And then we're also studying the combination of cannabis and HIV and how it affects the immune system of people with HIV, because a lot of people with HIV actually use cannabis. Now, I also have a group that works on interpretable neural networks. They're working on applications to neurology and computer-aided mammography. And these interpretable neural networks use case-based reasoning, where they have to reason about a new mammogram or EEG or whatever, based on its similarity to the training examples. So it's kind of like k-nearest neighbors, but you're only comparing parts of neighbors to parts of the test points using a learned distance metric. So I can't resist going into a little more depth on interpretable neural networks. And so the way it works is that they create a score for how much each part of a test image looks like part of the training image. So for example, if you're trying to classify why this bird is a clay-colored sparrow, the network would say, because this part of the bird, so highlighted in 2 different ways here, this looks like this part of that bird, and this is a prototypical clay-colored sparrow that's in my training set. And so it would say, this looks like that, this looks like that, and this looks like that, and it gets points for each of those comparisons, and it adds them up. And so you can see, like, it's like maybe the color of the belly and the edge of the color of the edge of the wing, and so on. And we do the same thing for mammography. So, you know, this particular breast lesion, we're trying to figure out whether to biopsy it. Then we say, oh, this looks like this, you know, case that we've seen before. And so we're going to add some points to malignancy score and so on. So it's kind of like K-nearest neighbors. Okay, we're also working on heart monitoring with wearable devices. So like your smartwatch, it's monitoring your heart. And as well, I have a student who's an expert in music theory, and we're working on interpretable AI music generation. This actually does not use neural networks. It actually uses music theory and other types of AI. It's totally interpretable. And all of these, you know, all these topics, these things are like super interesting, and it just shows a hint of what you can do with interpretable AI. All right, so just the takeaways here. A vast number of real-world problems do not benefit from black box models. They do not, they cannot, and they never can. There's both empirical and theoretical evidence to back that up, including a proof that like interpretable models should exist for noisy problems. I think regulation is needed to prevent abuse in high-stakes problems because companies like to inflict black box models upon people in high-stakes situations. And AI also holds endless possibilities for brightening our world and helping us to make better decisions by aiding us without replacing us. All right, thank you very much.
Thank you very much. Yeah, so actually I have a question.
Mm-hmm.
So how do you think we are gonna be able to regulate like the use of black box models for high stakes decisions? So how do you define what's an interpretable model over a like a non-interpretable model?
Yeah, so you and I were discussing this earlier, that evaluation of things is anything related to machine learning is difficult, but at least one decent proxy for interpretability is sparsity. So I was talking about sparse models because humans can handle 7 plus or minus 2 cognitive entities at once, right? This is a famous paper. Like the 7 plus or minus 2 paper back. So sparsity is a really good measure of interpretability. So, you know, you should at least have the models be sparse if they can possibly be. And then you can debate on which variables get included. So that actually simplifies the debate a lot about whether, you know, and how those variables are combined. But it's really, really domain dependent. So every type of evaluation, you know, what evaluation measure you use for any kind of machine learning problem is based on the application. So like classification accuracy, people don't usually want that. Like it's usually some balance between false positives and false negatives, or you've got some kind of calibration loss that you really care about. And it's the same thing with interpretability. It's really, really domain dependent.
I see. That makes sense, yeah. And yeah, I think at least my view is that nowadays a lot of people are still using like explainable model like methods, right?
Yeah.
And how do you see this? Is any hope at some point?
I'm not seeing it yet. I mean, I'm still getting this annoying situation where, you know, like for example, we submitted a paper a while back on the FICO data set. It was, I mean, granted it was a while back, but you know, we submitted it to a special issue of a journal, and the editor said, "Oh, we don't want your paper." But and I specifically emailed him and I said, "Look, we constructed models for the FICO data set that are just as accurate as black boxes, but they're really, really small. They fit on an index card." And the email I got back was, "Well, we don't really want your paper, but could you tell me where that FICO data set is? Because I'm working on explanations of black boxes, and I really want to explain my black box on that FICO data set." And I was just like, oh my gosh, like I just told you that you could there's interpretable models for that data set. Why are you doing this? You know, and this wasn't someone from some crummy institution. This was from like Stanford or Berkeley or something like that. Like it was, you know, a professor at those places. So, I mean, I don't know if things have changed at all, but the truth is, like, you know, before 2016 or so, interpretability was valueless. Nobody cared. Like all my students from that time, they were like, "Hey, Cynthia, do you remember when nobody cared about what we were doing?" I was like, "Yeah." And then it all became like black boxes with explanations, and I was like, "What? Interpretable models?" You know? So you know, but at least to be honest, at least there's like a category where we could get reviewers at conferences that care about explainability, even if they don't care about interpretability. But yeah, the extent of work in interpretable modeling still is, you know, it's pretty small. There's not too many people working on it. There's a little cult of us working on Rashomon sets. I had some friends and former students who brought this idea to other institutions. And so there's a group at Harvard that's working on Rashomon sets. And there's a group at Google working on Rashomon sets because of personal connections that got interested in it. But yeah, not too much in the way of like most people are doing this black box explanation crap. Yeah. But the quality of work in that field is so bad. I don't know why people want to do it. I mean, maybe they want to do it because it's easier. Like it's definitely easier to like poke at a black box than to replace it. So maybe that's what it is.
Yeah, I think that's what I was going to say. It's like if you want to just explain your model, there are many packages that you can just like. Is there like any package that I can use to fit like interpretable models?
Yes,
Like,
I mean everything that I presented is all publicly available. So
yeah.
Fast Sparse, Ghost, Tree Farms, Faster Risk, all of them have packages that many people have used, you know. So every year I give it to my students and give them an option to use it. I have friends who handed it to their classes at other universities. So it's not like it's raw stuff that nobody's ever used. Like you can use it, and if you have any trouble with it, our students like are happy to help you troubleshoot whatever the issue is, which is better than you can say for a explainable package, you know.
Yeah. That makes sense. Yeah. Does anyone have questions for Cynthia?
It's very quiet today.
Yeah.
I can actually ask one other question. That was really interesting talk. Thank you again for presenting. One thing I was wondering when I was listening to the additive tree model, so it is also true that when we change or we take a transformation of our covariate, it becomes less interpretable, right? For example, if I do some kind of kernel regression, or I do some transformation of the input covariates. So do you think that is kind of allowed?
Well,
Just a general opinion.
I don't agree with that. So I'll show you why I don't agree with that. I'm going to go back to the very beginning of the talk. So let me just go back here. I have to click back all those clicks that I did. Okay, here we go. So I'm just going to put up the fast sparse model here for the FICO data set. So this model here. So when you're allowed to do nonlinear transformations of the original variables, it actually makes it a lot more interpretable sometimes. So for instance, if you have a disease that really only hits people as they're having a growth spurt or something, like it only hits people during their teenage years, then what you want is that you want a nonlinear function of it. So you want it to go up while they're teenagers and then down when they're not teenagers. So you really want to have the ability to have the model be sensitive to certain areas, certain regions within a certain covariate, like over here. You know what I'm saying? So I actually think that having some nonlinear transformations of the variables makes it more interpretable.
I see. So you were saying that we can sometimes allow the kernel regression type of transformation also, and then let's say fit a sparse additive tree after transforming the variable.
So it depends what kernel you use, because most kernel, like Gaussian kernels, that is not interpretable.
Yeah, that's actually what I had in mind. Yeah.
I mean, unless you want to do unless you want to do some kind of kernel that's like, K-nearest neighbor kernel, something
like simple
like
kernel, interpretable kernel.
Yeah.
Yeah.
Mhm.
Yeah. Anyway, thank you. Thank you very much. Yeah.
Sure. Okay, so there's a question here on transcriptomic data. So all of our dimension reduction work is on transcriptomic data. And like we actually specifically have a paper on like evaluation of dimension reduction on transcriptomic data. We also have a lot of decision tree stuff on genetic data. So this HIV and cannabis project that I mentioned uses like yeah, this kind of data. Okay, sorry, what was the next question?
I think Felipe just made a comment here in the chat that faster risk is just what he was looking for
Great.
for months.
Yeah, let us know if you have any trouble with it at all, and we're happy to help you.
Yeah. Any more questions?
I have a question. Can
Mhm.
you hear me?
Yeah.
Hello. Yeah, thank you for the fascinating talk. It was very stimulating. I had a question about these Rashomon sets in high impact decision making, where you have like my understanding of it is like you have a model, and then if the model like gives you some kind of outcome, then I mean that's your outcome based on like whatever the model gives you. But if you have like a family of models that may disagree on their outcome on you, then I guess like you have to figure out some way to aggregate those outcomes. And presumably you have some kind of distribution on how you weight those models, maybe. But if you have a different, maybe there's a weighting for my data point, but then there's another person, and maybe there's like a different kind of weighting, and what is the right way to, I guess, weight the Rashomon set? Or I don't know if that's the right way of.
So you're thinking exactly in the right direction, because the Rashomon set is a bunch of models that are indistinguishable with respect to the data set. And so the question of which model you choose, it's not going to be answered by anything that is really in the data set. As far as I know, because like, you try one ghost model and it doesn't matter which, well, which model ghost returns in the Rashomon set then seems to perform pretty well on a fixed data set. So what you really need is some domain expertise to tell you which of these models is actually going to work, robustly in the real situation, right? Because there's no way to distinguish between the models other than domain expertise.
But sorry, I have one other kind of vague question about this too. So you train maybe a classifier, and then you get your family of models. But that classifier was trained on some training data obtained from some population, and like if that training, the distribution of like a different training set would maybe give you a different family. So
Yeah.
some kind of like how do you account for that, the randomness in your training data that created your Rashomon set? It seems like there's like a a larger grandparent family of Rashomon sets based on the randomness of the training data too. And is that
Yeah, so that's kind of like what our variable importance stuff is trying to get at, like if you can do bootstrapping and look at all the Rashomon sets from the bootstrap samples. So those students actually tried to do kind of what you're suggesting, which is like, okay, let's bootstrap sample a whole bunch of times, get all the Rashomon sets, find models that seem to be in all the Rashomon sets, right? But it didn't work any better than a single ghost model. So ghost, just one model, like I said, on a static data set, it just seems to be fine. So yeah, you're stuck with domain expertise at this point. Like you don't know which way the distribution shift might happen. And if you knew that, then you could figure out which models were likely to generalize.
Thank you.
Sure.
I think there's one more question, but we are also running out of time. So
Okay. Interpretability flow from the model through
So new.
deduction onto certain RNA value. I don't know. Don't ask me about genetic data. I don't. I'm not a biologist. I have collaborators for that.
Okay. Yeah. Thank you very much, Cynthia. That was amazing talk. Yeah, I really liked it. Yeah. Thank you very much.
All right. Good luck to you guys.
Bye.
Thank you. Bye.
Thank you very much. Bye.
Bye.